This meeting is being recorded. What's today, the 22nd? So we have 3 lectures to get through some stuff before we have our 5th exam. So I guess I'll just start going in because some of this can be pretty straightforward, but we are going to start pulling things from previous knowledge. So we might have to do a little brushing up on that. What I want to talk about, oh, get my glasses here. What I want to talk about today is solutions. So, oops, oh, I forgot I was doing office hours in a different pen. So I need to get these the right size. All right, let's try this again. Solutions. When we talk about solutions, what we're really talking about is a very specific type of thing. A solution is a homogeneous mixture of a solute dissolved in a solvent. And if we remember this, I think we have talked about solutes and solvents in the past. The solute, this is the thing being dissolved. The solute is the thing being dissolved. That means the solvent is doing the dissolving. And it should be noted that it is the lesser amount. Now, this goes back to our homogeneous and heterogeneous mixtures, as it were. There is no way to make a heterogeneous. Solutions, by definition, have to be homogeneous. That is their classification. But within solutions, there are 7 different types of categories of solutions. So let's look at the categories that solutions can be placed into. So there are 7 categories. Seven categories of solutions. The first set is going to be a gas dissolved in a gas. Now, it's usually when we think of solutions, we think of watery stuff, but you can have gaseous solutions, and later on we'll see actually solid solutions. And so sometimes you got to put some of your preconceived away. We just want to think about something being dissolved or mixed inside, right? So dissolving could also just be a mixing, depending on your point of view there. A classic example of a gas dissolved or mixed inside of another gas to make a solution is good old-fashioned air. And there you have oxygen dissolved in nitrogen, because oxygen is 21% of the air, nitrogen is 79% of the air. So oxygen is the lesser amount of what comprises air. So we could consider that the oxygen is the one dissolved in the nitrogen. If there are any scuba divers in the house, when they do their gas mixtures, if you're doing some deep diving, they will actually call that either the gas mixture or the gas solution. So they are dissolving other gases inside of there to make sure you don't get any bad juju when you go down that far. Another type of solution that we have that involves gases, this one's actually seemingly strange and yet very, very common. And that is you can have a liquid dissolved in a gas. That seems kind of weird to think of a liquid being dissolved in a gas. And it is weird until you realize that the example of this is fog. And there you get tiny water droplets dissolved in air. So for anybody who has extremely short hair like I do, whenever I would go for a run in the fog at Bakersfield, loved running in the fog. It was one of those fun phenomenon that as I would get a mile or two in, I could reach up to my hair and find tiny little water droplets just clinging to those little hairs sticking off the side of my head. And that's because as you're running through fog, it's actually very, very tiny water droplets that are suspended just by the heat of the ground, creating a hot buoyancy, lifting them up instead of letting them settle into the ground. All my little tiny hairs were basically acting like a comb to grab them out of the air. It was actually kind of a fun thing. I always enjoyed reaching up in the middle of my run and going like, wow, look, water everywhere. And it wasn't my own sweat because it was nice and cool. We have some other solutions. These are going to be a little more familiar to you, and that is a gas dissolved in a liquid. That one's going to be a little more familiar because we see it every day. If we think about sodas, there you have carbon dioxide dissolved in water. Now, it's kind of weird to think about that. Hold on a second. Oh, I don't know what that was. It's kind of weird to think about it being dissolved, but again, the word dissolved, you could substitute the word mixed. And carbon dioxide does mix into water, especially if you put a bunch of pressure on it, you can actually push more and more and more CO2 into it. Of course, as soon as you crack the seal on that, the CO2 is going to try to leave. We discussed that in the intermolecular forces section. But we do know that you can get some carbon dioxide to dissolve in water. And some of it will actually permanently stay. The next one that is probably very familiar is a liquid dissolved or mixed, if you will. A liquid dissolved in a liquid. And here you can think of any alcohol. Vodka. Right, this is ethanol in water. So beer. They say it's 5%. 5% of that is alcohol. The rest of it is water. And finally, the last one here, we have a gas into a liquid dissolved into a liquid. We can have a solid dissolved in a liquid. And of course, this is good old salt water. So those three shouldn't be anything too unfamiliar. The last two might be interesting, although we do know one of them, even if we haven't thought of it in that term. One that's a little strange here is a liquid dissolved in a solid. We just got through seeing a solid dissolved in a liquid, salt into water. That's pretty much a no-brainer. But there are very, very few situations that do happen where a liquid can actually be dissolved or subsumed or otherwise mixed into a solid. The most common one is the amalgam fillings. And this is where you have liquid mercury in solid silver. These are those so-called silver fillings in your mouth. So these are the silver fillings. Again, kind of a rare case, but they do happen, and it is technically a solution made of those. And that solution is actually called an amalgam. And finally, the last one that we do know, even if we didn't know that, is a solid, solid dissolved in a solid. And that goes all the way back to our alloys. So we've got like copper with tin to make bronze. I think bronze or brass. I always forget which one is which. Now, as we look at all these 7 different types, clearly the ones in red, kind of not that familiar to us. The ones in green, kind of not that familiar to us. And so let's talk about the ones that we really know, and that's these guys here in blue. We're going to focus on these. Mostly because we can actually wrap our heads around it, and they occur around us all the time. So when we look at a solute dissolved into a solvent, that has everything to do with intermolecular forces, and there are factors that will actually affect each of these abilities to dissolve into each other separately. The first one I'm going to talk about is the gas dissolved in a liquid. So one of my longer titles ever is going to be factors affecting gas solubility in a liquid. And yes, intermolecular forces play a part in this, but since most liquids are held together by some sort of dipole-dipole interaction or things of that nature, and since most of the gases that we have are nonpolar in nature, those interactions are very weak. So we won't talk about those there. What we're going to talk about instead is how temperature and pressure affect them. And for this, I guess I should have moved all those down a little bit. I want us to, when we do this, I want us to think soda. Now, if we think of this in terms of the sodas that we might drink, we have to think about how we like to drink them. First of all, we like to drink them when they're cold. I can't think of anyone that likes to drink a warm soda. And there's a reason. Sodas are very appealing to us. They have 2 of the main food groups that humans love. We like sugar, salt, and fat. Sodas have sugar and salt in them. So one of the things is that we like is, sometimes they have salt, I should say. Most of the time it's the sugar. But if you get something too sweet, you have to balance it out. And one of the ways they balance it out is by doing the carbon dioxide injection into it. That creates carbonic acid, and carbonic acid is actually sort of very pleasing to the palate. And so that acidity will actually balance out some of the sugary aspect of it, which means, guess what? They get to put more sugar into it and make it even more addicting, as I take a sip of my Dr. Pepper right now, as if to reinforce that. Now, if we think about sodas being cold, and we think of the fact that they want that carbonic acid, they want that CO2 plus water making H2CO3, they want that to be in the water as long as possible to make you keep drinking the soda. We can think about this as the temperature increases, okay? So we have cold sodas, we like that aspect of it, and we also like cracking open a cold soda, because when we do that, nothing happens. But if you've ever cracked open a warm soda, you do know that something very drastic can happen, And God help you if you open it over your mother's favorite rug. When you open up a warm soda, that thing explodes. And that's because all of that carbon dioxide that was trapped inside of the water wants to get out as fast as possible. And if we think about what temperature means, remember that temperature is the average kinetic energy of the system. So remember, temperature was the average kinetic energy. If we think about that, as the temperature goes up, we have given those gas molecules more and more energy to move around and to try to get out of this watery environment that they don't like. So as the temperature increases, our gas solubility actually goes down. So that's one of the reasons why we like to make our sodas cold. It keeps those molecules slowed down. It doesn't give them the energy to get out. And that way we have that sort of acidic taste when we're trying to balance out the sugary stuff. So as the temperature goes up, the gas solubility in liquid goes down. Now, if we think about the next one, pressure. Pressure is actually another way we like to drink our sodas. Nobody likes to have a soda that's been opened up and been sitting around for a day or so. It has no bubbles left in it. And that's because, remember when you open up a soda and it goes, right? That is you releasing all the pressure of the carbon dioxide that has been built up inside of there, or actually put in there, to force those carbon dioxide molecules into the water. So they pack these sodas nice and cold. They pack them with a whole bunch of carbon dioxide pressure inside the bottle. And that is to make sure that that CO2 gas stays in the liquid where they want it. The more pressure, the more you can shove those gas molecules in. So as the pressure increases, the gas solubility also increases. The more pressure, the more you can shove them in. So while they don't have very strong interactions in general, because you're usually talking about nonpolar molecules trying to get into a polar solvent, they do have limited solubility, but there are ways of actually affecting it. And one of the easiest things to do is to drop the temperature down and pump the pressure up. You'll be able to shove more and more of those gases in there. Now, that's pretty straightforward. Let's talk about factors affecting liquids with liquids.
Hey, Forrest.
What affects? Yes.
Just a quick question. So this is carbonation and sugar. So this is CO2, water, and sugar. Is this the same as like fermentation? So if you think about like a champagne or a bubbly, or is that different because of alcohol?
It absolutely goes with alcohols as well. You know, right now I've got my beer getting force carbonated, as we say it in the biz. If you homebrew and you're doing it in bottles, you typically, as you rack the beer into the bottles, there's just a little bit of yeast still alive in there, and you put in just a little bit more sugar into each bottle, and you cap it off. Those yeast eat yeast eat the sugar. They poop out their little CO2 as their byproduct, and they carbonate your beer inside of the bottle. They do the same thing with champagne. And so they ferment in the bottle there like that, and they pressurize the champagne just like that. I'm actually force carbonating mine. I racked them over into a keg. I said I don't want the yeast to do their job. I want to drink my beer in 2 days instead of 2 weeks. So I'm actually putting them under a whole bunch of carbon dioxide pressure from the tank and saying, get in there. I want my beer to taste good, and I want it to taste good now. So again, with your champagne, if you've ever opened a warm champagne bottle, you know that is a very dangerous thing to do. That cork will go crazy. You've given those bubbles in champagne a lot of energy to try to get out of there as fast as they can. And as soon as you release the pressure keeping them in, they will go out. There appears to be some sort of question in chat. Is that correct? What do we have? Sparkling wine is bottled cold and then pressurized into bottling. Yeah, you know, but the old school, Vincent, was to actually keep the yeast in there. I mean, if you think about the riddling racks where they would continually turn those yeast to try to get it to pressurize, to get the carbonation in there. And remember what they did is after they kept turning them on the riddling rack, it was to actually settle all of those yeast into the neck of the bottle, where then they could very quickly take out that little plug and shove in their little mushroom cap thing. It's all magic, but there were ways of keeping that CO2 in there. And I do recall it involving a temperature thing about freezing it up. But yeah, these days you can actually force carbonate a sparkling wine as well.
Yes, sir. That's method champenois.
Oh yes, sorry. Let me be very, very français about that. And actually, where is Sume to correct all of our français on that? Where are you, Sume? Oh, he's not here today. Oh, he would have totally got us.
No, I'm here. I'm listening, you guys.
You're listening to us butcher your language?
Yes.
Yes, and I will find you and hunt you down in your sleep. Yeah.
Hey, let's hear you say champagne.
We say champagne the same thing because it's a name, it doesn't change. But the same.
Yeah, it still sounds better when somebody who can say French.
Yes.
It's called Champagne. Y'all are saying it wrong.
That's right.
Okay.
So what affects liquids? Did I answer your question?
You did.
Reagan?
Yeah. Yes, you did. Thank you.
Okay. Is there still more people screaming at me in chat?
No.
Oh, okay. All right, what affects liquids and liquids? Since mixing with liquids involves all of our intermolecular forces, it is all about those intermolecular forces. It's all about the IMFs. And we talked about this when we talked about intermolecular forces, but we're going to reinforce it again here. Just remember that polar dissolves in polar. And nonpolar dissolves in nonpolar. Like dissolves like. It is a phrase that a lot of people use. And so as we look at this, let's take a look at some common polar solvents. Common polar solvents. Well, the first one, clearly, what do we dissolve everything in? Water. Right? We love to dissolve things in. Oh wait, is Winnie here? Where's Winnie?
Not present.
There we go. So we dissolve it in water.
Yes, water.
There we go. I'm working on it. Working it. All right, water, which I'm going to go ahead and write as HOH. Another common solvent that we like to use is ethanol. So alcohol, CH3, CH2OH. If you go back to the intermolecular force lecture. Well, wait, we can. Look at that. Bam. There's your water, your ammonia, and right there is your CH3, CH2OH, showing that it is polar. We might as well go ahead and throw some methanol in there. And that's CH3OH. Other things, since we had it there, ammonia. Oops, whoa. And that's NH3, again, very polar. And a couple of other things that we like to dissolve things in is vinegar, which is, I'm going to write as CH3COOH. I'm going to use the organic way of writing it. And I'm going to do a little isopropyl alcohol. And that'll look like C3H6OH. Now, these are some of the more common things that we like to dissolve things in. Another one is acetone as well. But hopefully it doesn't take too much imagination to see what's the main thing trying to make sure that these all dissolve. That good old OH or even the CO bond. We got a little NH, these OH. Our common polar solvents that we like to dissolve things into typically have that OH dangling out there on a very small molecule, 2-3 carbons long or no carbons at all. And they make the solvent very polar. So if there's anything else over there that is polar to any degree, they are going to jump on board and they're going to go ahead and dissolve. So it's all about that. So then what is a common non-polar solvent? That one's going to be interesting. That's going to be interesting and probably just a little bit harder. And in fact, in a normal class setting, I would ask people, do they have any common non-polar solvents?
Forrest,
Yes?
there's an off-topic question
Oh,
in your
thank you.
chat.
I don't see the chat popping up. What's the minimum percentage of isopropyl alcohol for it to be an effective hand sanitizer? Oh, damn. I don't even know.
Can you scroll down a little bit?
I thought it was 70. Didn't it say 70?
Well, so the isopropyl alcohol you have in your medicine cabinet, as it were, underneath the sink is usually where most people put it. That is 70% isopropyl alcohol by volume. And so it looks like, well, if 70% of it is the isopropyl alcohol and only 30% is water, how can it be that the alcohol is dissolved in the water? Remember, I said it's by total amount. They do it by volumes because it's easier for them to think of it that way when they manufacture it. But if you actually get down to the atomic level and the percentages by mass, there's actually more water in there by mass than there is by isopropyl alcohol because of its density. That 70% will definitely kill a lot of stuff. I don't think you have to get that concentrated to kill things. But hey, if you have 70%, why not just use it and be safe if that's what you're doing? If you're trying to make a hand sanitizer out of it, I want to say that it's 25% is what some of them are. Well, hey, I have another computer. I could probably just look it up. What is
Minimum
the,
Oh, I just Googled it. It says it must be at least 60%. This is according to CDC. At least 60%, but aim for a minimum of 75%.
wow, so they're going like full on Everclear on us, right? Jiminy. 60 to 75%. Why don't you just whew.
Just throw some moonshine on your hands.
Right, exactly. Just man.
No, don't waste the moonshine.
Vodka or tequila is also faster.
What did you say, Sume?
Vodka or tequila is also good.
And then, actually, in case there's another wave of hoarding going on, yeah. Yeah, if you want to slowly stock up before the winter resurgence, I would say get a few bottles of the isopropyl alcohol and just get them around. But social distancing, guys, let's flatten that curve and stuff. All right, back to the common non-polar solvents. These are actually, as far as being common, they're there as being common in your lexicon and everyday life. Not so much. In the lab, you guys, oh, no, you didn't see because we had to do it remotely. When we were doing the anion test for lab 5, I think, 6, something like that, we had hexane. That was the layer that we floated on top of the water to trap the diatomic chlorine, bromine, and iodine. That is a C6H14. For anybody who works in any sort of paint or stuff, toluene is another one of their solvents. It's often found in paint strippers, and that is C7H8. And anyone whose family's in the clothing business, you might remember this guy, carbon tetrachloride. And that's CCl4, and that is the so-called dry cleaning. It's actually hardly used anymore, not used anymore, really, because cancer. Now, each one of these you'll notice is nonpolar, whether it's because it's all C's and H's, or if it happens to be this carbon tetrachloride, which is tetrahedral, and so therefore nonpolar just by its symmetry and its shape. Each one of these has a usefulness, although it being very limited. And the reason why we won't have, off the top of our brains, a lot of nonpolar solvents is because typically the things that we want to dissolve are things that we want to put inside of our body. So, AKA, get it inside of water or alcohol or vinegar or something so we can eat that stuff. The nonpolar stuff we really just don't like to eat. I can't imagine anybody who just loves to go over to that vegetable oil and chug it. I dare you, and we'll see what happens on the back end, as it were.
Is that cadmium 14?
What?
Is that cadmium 14 or CC 14?
CCl, carbon tetrachloride. Remember the naming? So you're going to have 4 chlorines. I'll write it a little more clearly. I don't know if that helps. I don't like that L. You know, when it comes down to it, if anyone's ever actually worked with some of these non-polar solvents, especially something like toluene or turpentine or the like, they always tell you to wear gloves because, you know, they're non-polar solvents. And guess what? Your skin is also non-polar. How do we know that? Because when our skin gets wet, it doesn't dissolve, right? So if our skin were a polar thing, it would dissolve as soon as we got wet. So our skin is non-polar. So if you get a bunch of good, strong, non-polar solvents on your hands, you're going to have a bad day. When I worked in the oil fields for my first couple of summers, well, I should say my 3rd and 4th year actually in college, I worked in the oil fields. At the end of the day, when we come home and come back to base and we would start scrubbing up, a lot of guys were taking a little bit of a shortcut. And that shortcut was to take this spray that they called Chem Tool. It's essentially an engine degreaser. and they would spray this engine degreaser all over their hands. Meanwhile, I'm sitting over there with a bar of lava soap, just like scrubbing away and scrubbing away and scrubbing away, and they're just kind of laughing at me because I'm not taking this shortcut. And I was just like, you guys are really not doing, so, this is not good. You look down at their hands, and not only was it taking the grease off, but their hands were getting like this white film stuff on them. And guess what that white stuff was? That was the fats inside of their hands actually leaching through their skin, getting dissolved by this super heavy duty non-polar solvent. And that's the other reason why you walk around and most of those guys had like these leathery cracked hands everywhere. They had basically zero fat left in them to make them all pudgy and nice. And they were just abusing the crap out of their skin. We don't in general like non-polar solvents because again, what we do is we dissolve stuff to put it in our mouth. So there you have that. It looks like there's some more chat stuff here. What do we got? Okay, you guys are doing all that. Okay. So basically, quick little thing is, oops, will these pairs mix? And when we look at this, I want us to always ask yourself, will it dissolve in water? Okay, so when we do these, because you may have never heard of these, or even if you have, you may be like, well, but I don't really know. You didn't give me the chemical composition of it. How am I supposed to know if it is polar or not? The answer to that is, does it dissolve in water? So, or as when you would say water. So first I'm going to say H2O and vinegar. Will those mix if we put them together?
Yes.
Yes.
Yes. Okay. Okay, I always start with the ones that should be there. But again, if you actually had it, you would see up here, we have this COOH, and we have this OH right there. Both of those will want to make it polar. Therefore, they will get together. Now, let's keep with the easy ones, and then let's go to thinking. Water and oil?
No.
Oh,
No. Okay. Let's step it up another notch. Vinegar and gasoline.
yes.
This is a no. Now, why is that a no? That's a no because while vinegar is definitely polar, gas is non-polar. Now, how might you know that gas and water don't mix?
Oil and water.
Yes.
Because oil and water, right? So again, you want to go through to your life experiences here because oil and gas, they very much do want to mix. You know, right now they talk about the oil prices going crazy, stupid low, and they're talking about propping up the quote oil and gas market because those two things go together. You refine gasoline from the oil we pump out of the ground. If those two things didn't like to mix in the first place, they wouldn't be found in the same place. So oil and gas like to get together. You know that oil is nonpolar, therefore gas has to be nonpolar, right? So you know that oil is nonpolar because oil and water don't mix, right? So that means that gas is nonpolar, which means now if that's nonpolar and you know that vinegar is, those two things won't get together. So sometimes you have to be creative. Let's do something like paint and water. And let me be a little more clear. The paint for your house, not your little watercolors that you're making your little stuff about.
No,
No. And why do you say no?
because when it rains, it doesn't melt off your house.
Yeah, when it rains, it doesn't melt your house, right? Now, but what about this? Can I do paint and gasoline? Will those two mix?
Yes.
Yes. And in fact, in a pinch, I have decided to strip the paint off of something with some gasoline because I didn't have any mineral spirits, which is essentially gasoline, to strip off the paint. I just wait a long time for it to evaporate off. And again, all of this is, will it dissolve in water? And if it does dissolve in water, that means that it is polar. And you're again looking for the like dissolves like. So look for like dissolves like. And it all goes back to those intermolecular forces. Okay. Let me just see real quick. Did I put a big line? Nope, I didn't. All right, so what affects solids in liquids? Well, it is just like with liquids and liquids. Just as with liquids in liquids, it is all about the intermolecular forces. All right. Now, basically what that boils down to is polar, or if we're doing solids and liquids, I guess I better do it here. Ionic with polar solvents and nonpolar with nonpolar. So that's what we're going to be looking for there. So an ionic with polar, of course, we're talking something like NaCl with water. You got that ionic compound with a polar. Two nonpolars may be something like grease with gasoline. So grease being a big, thick, sticky, solidy thing, you can dissolve it away with gas. Just pour it on and melt it away. So let's take a look at some pairs and see if it will or will not work. And of course, we did just say that one, so I'm going to do something like Na3PO4 with H2O. Will that mix? Oh, I guess I should put a heading. Will it mix? Hold on. Oops. Will these mix? Sodium phosphate with water. This will mix because we have an ionic with a polar. What about sugar with water? Will these mix?
Yes.
Hopefully, obvious answer. Yeah, of course it will. Yeah, but is sugar ionic? I have a C6, H12, O6 for sugar.
Yes.
Oh, no, it is not ionic at all. And in fact, man, I'm probably going to get this wrong, but as I recall, one, two, three, four, five, and I think one of these, I think is a C to an OH. I think we have an OH, and an OH, and an OH, and an OH coming off like this. I think that's sugar. It's something like that. I guess I should look it up if I'm going to put this in my notes. All right, let's go look it up. Bam. Let's go here. Let's do sugar structure. There we go. No, I just put the OH in the wrong spot. So it's pretty close. There we go. Let's just do glucose. There we go. See if I can copy that. Copy image. Go back over here. Paste it in because we can. Oh, I probably can just do this. What? Ah, forget it. Oh, wait, I did draw it right. Anyway, that aside, I think that was you, Massey, that said it was ionic. It doesn't actually break up into ions, but hopefully you can see that it's definitely polar because we have all of these OHs hanging out to make it polar. So while this isn't about ionics with polars, this is still polar with polar. So even if you didn't know that structure of sugar, you just knew instinctively if I dropped it into water, it's going to dissolve. So I do want you guys to always keep in mind what you're dealing with. Use your life experiences as much as possible. What if I have sugar with oil? That's not going to work because here we see a polar with a non-polar. I guess I should have put that over here. Polar with the non-polar. Of course, we know that oil is non-polar because oil and water don't mix. We know that sugar and water do. So those won't work. Let's do some of that grease with that toluene.
Yes.
Yes, absolutely. So if you just went back up just a little bit, we said the common nonpolars, hexane. We know that grease doesn't come off if you just use water. So those are both nonpolar. So that's a non with non. Iodine with hexane.
No.
Yes. Now, iodine, remember iodine is I2. There are 7 of these. What do we call them?
Diatomic molecules.
Yep. And those absolutely, by their symmetry, are completely nonpolar. So because they're nonpolar and that hexane is nonpolar, here again we have a nonpolar with a nonpolar. And of course, from the lab that you guys watched, we did trap the iodine in that hexane layer. And finally, I'm just going to do this one because it's in my notes. Sugar with gasoline. Nope. Because sugar dissolves in water, gasoline does not. So we have a polar with a nonpolar. Now, as we look at this, we've sort of discussed what it means to want to make a solution. When you do it, it will be homogeneous. It will be the same throughout. And why do they want to mix in the first place? It has to do with their intermolecular forces. Now, that is just, will you dissolve or will you not dissolve? It's not talking about the speed of dissolving. Okay, that's a different issue. So you might take one thing and dissolve it, and yeah, it dissolves like super, super fast. And another one takes a long time. Time to dissolve does not affect the fact that it does dissolve. So let's talk about speeding up. So now that we've talked about will it or not, so now that we have talked about whether or not it dissolves, let us talk about how to speed it up. It's one thing for us to talk about does it or does it not dissolve in the first place. Then there is making it go faster. Now, what I'm about to show you is not necessarily is basically taking any system that you have that naturally would want to go and dissolve and make a solution. Now we're just going to speed it up. This has no effect on if you didn't want to go in the first place. We're going to make you. We're just going to talk about speeding it up. Now, there are 3 ways to speed up a mixing process, and those are to heat it, to stir it up, or to grind it up. Now, basically, the heating is probably a no-brainer, right? This is hot tea versus cold tea or iced tea. Which one dissolves that sugar faster?
Hot.
Absolutely. Sugar dissolves faster in hot tea. That's a no-brainer. Now that we know the intuitive, remember I told you at the beginning of this class, I'm not going to tell you anything you don't know. I'm just going to tell you the why. So let's talk about the why. Remember, if you're heating it up, you are increasing the temperature. If you heat it up, you're increasing the temperature. Now, if I'm increasing the temperature, what am I really increasing? The kinetic energy. And what that's going to allow us to do by increasing the kinetic energy is the molecules will move faster and there are more chances for them to ask that solid into solution. So more movement. This is more chances to try to ask the solute into solution. So stirring. Right? You have the cold tea or the iced tea, sorry. Stirring iced tea.
Forrest,
Yeah.
what about like adding salt to that? Like for,
Adding salt to what?
for heating it. Like when you're like boiling water and you want to make it boil faster.
Yeah. So that's a slightly off topic, but I want to go ahead and address that in just a moment. How about we do that? Let me get through the heat, stir, and grind, and I want you to ask that question again.
Okay.
Because it's a neat little fun fact that at least two of you are going to like, and so I'll tell the two of you this really cool thing. All right. So we all know that if you want your sugar to dissolve faster, you're going to put it in the hot tea versus the iced tea. But you still want your sweet iced tea. So what do? You dump in your sugar. It goes straight to the bottom of the container, and then you stick your wooden spoon in there and you whip the crap out of it until it finally goes into solution. Now, all you're doing there is increasing the speed at which it goes in, not making it do something it doesn't want to do. It does want to do it. It's just going to go about it slowly because it doesn't have a lot of energy to get into the solution. So instead you stir it. So you stir the iced tea to make it dissolve faster. And again, why? Moving the molecules. Moving the molecules mechanically also increases the chances for the solvent to ask the solute into solution. Basically, instead of waiting for those water molecules they are moving, right? They are moving around. They're a liquid. They're slipping past one another and doing their thing. They're moving around by something you might call Brownian motion or the random walk. They basically take a step in any one direction, and you may step away and step toward or step to the side of that solute you're trying to ask into solution. But if you're relying on something to take one step forward and two steps back and come back and try to get into solution, you're going to be waiting a long time. So instead what you do is you mechanically move those solvent molecules over and over and over those solute molecules. And basically, instead of one person trying to ask the solute into solution, you drag 50 billion of them to constantly nag that solute to get into solution. And so by sheer numbers of interactions, you will now increase the ability for that solute molecule to get into solution faster. Finally, you can grind things up. All right, this is rock salt versus granulated salt. Hopefully it's not too much of a leap to know that we like to take granulated salt and sprinkle it into our food or add it as a seasoning as we're cooking or anything. You can use rock salt, knock yourself out, but good luck getting it to dissolve into anything that you want to cook with. And that's because by grinding, what you end up doing is you increase the surface area. Increase the surface area, AKA the places that the solvent can reach. You're going to increase the surface area, the places that the solvent can reach. This means, again, more interactions, which means more chances. You can put rock salt into water. It will eventually dissolve. Or you can put granulated salt, the salt that you and I all know and love. You can put that into water and watch it disappear pretty fast. So heating and stirring and grinding, these are all things that should be no-brainers. We knew, now we know why. Go ahead and ask your question there, April.
The like heating, like adding salt to make the water boil faster.
Okay, that is a myth. So a lot of people grew up and grow up right now, and they will continue to grow up with someone in their family teaching them how to cook pasta, and they take their water and they put a sprinkle or more than a sprinkle of salt into that water, and they'll tell you it's going to make the water boil faster. That is false. Now, oh, is someone going to try to challenge me here in the chat room? Is that what's going on? Oh, I see a flash. Oh, someone's going to ask a different one, not challenging me. All right, Reagan, is grinding the surface area, volume area, what the heck does that mean?
The ratio. Is grinding the same as, is it using the surface area to volume? Oh, ratio. We learned that in bio.
Yes.
Just like it's just so small.
Yes.
Okay.
Yes, it's exactly the same. So
So
adding that salt to the water. Go ahead. April?
okay, so do you remember when you had your second baby? And we had that lady, what's her name?
What did Heidi cover me or Frenny?
I think it was Heidi.
Short and frenetic or tall and ambular?
Short. With short hair.
Okay, yeah.
Okay, so she said
Yeah, okay.
that increasing temperature adds energy and then breaks bonds with H2O/H2O plus Na plus Cl negative. So salt.
Okay, sure.
So that's what she told us. And then you're telling us no.
I know what she's talking about, and I'm gonna address that, and maybe it'll clear it up for you.
Okay.
Massey says, I heard adding salt to pasta water creates a more even boil and also flavors the pasta, but not boiling faster. The even boil is also incorrect. That only is flavoring the pasta. So here's what happens, and here's how the myth gets perpetuated. And so I'm going to tell you right now, you only add salt to flavor your pasta. I believe, Meng, are you in here? Yeah.
Yeah.
So Meng is aware because we did the calculation in Chem 121. If you add salt to water, yes, you can increase the temperature at which the water boils. And if you increase the temperature at which the water boils, you can cook your stuff faster. The problem is you have to use so much salt, it is ridiculous. Come to Chem 121 and we'll talk about it. You add salt to water merely to flavor it. It will not make the water boil faster. It will not do any of that. This myth comes out because inherently somebody is starting to boil water. And they're pumping in heat, pumping in heat, pumping in heat. And then they go like, oh my gosh, I forgot to add the salt. And so they pour some salt in, and it appears to boil for a split second. And they're like, oh my gosh, I made it boil. And then it usually simmers right back down to where it was, and you're like, ah, it's not boiling anymore. What has happened there is that some of those gas molecules that are trying to be created because you're pumping in all that heat, some of them are just a fraction away of being able to get away to get out. Now, we didn't get far enough into, oh no, we did. We boiled the methanol. If you go back to the boiling methanol experiment, we talked about the boiling chip. Now, the boiling chip is a foreign body that you introduce into your watery solution or your methanol solution or whatever. And what it does is it creates a spot for those gases to gather around each other and make a bubble and get out of solution. Gas molecules cannot just randomly form in the middle of your liquid. Those liquid molecules will say, hell no, we're not doing this. You can't do that. So instead, the gas molecules find something that doesn't mind them sticking to it, AKA the pan, AKA a boiling chip, and they will start amassing themselves on that foreign object, and the water can't tell them anything because the solid's like, look, I'm giving them a place to sleep. You stay out of this. Once those gas molecules are big enough, they will form a gas bubble and then run to the surface. When you dump the salt into nearly boiling water, before they dissolve, they act like a boiling chip, and so it looks like it's boiling, but it really isn't. In fact, if you put in like, what was it? It was like 2 or 3 tablespoons of salt into just a couple of quarts of water, you'll raise that boiling point 0.02 degrees. You're not doing anything to it. You are merely putting the salt in there to flavor the water, to flavor the pasta. That's what you're doing with that. Does salt lower the freeze? Oh, yes, Mr. Midwest himself. You're talking about and what I'm talking about is something called the colligative property. Adding salt into water will raise its boiling point, although I've pointed out that it doesn't do that very well, but it's very effective at lowering the freezing point. What it does do is suppress it just enough that it will melt, because instead of freezing at 0 Celsius, it might freeze at -2. And that just a little bit of difference will start to melt the ice and make it slushy, and now you can drive on the roads. Every solvent, water, alcohol, you name it, they have their own ability to be influenced by these particles, and it's an empirically derived value, and not all things occur the same. So it's not like if you raise the boiling point by 3 degrees, you'll lower the freezing point by 3 degrees. That's not how it works. It's a very asymmetrical and very situational dependent situation. If you want to stick around after the lecture, I'm more than happy to talk to you more about it, because it is kind of cool and fascinating.
Yes, because I have a couple other questions like that that are kind of off topic.
Yeah, and these off-topic questions are actually pretty cool. But it's one of those that if we just stay in the Zoom afterward, we can chat about it, and I can pull some stuff up and show you. But since we're almost done, I think I want to talk about saturation real quick, and our last time about percents, and then call it a day. Let's talk about saturation. Now, saturation is something that we're all familiar with, but basically, when you got enough in there, when you have all of your solute in there. Now, it turns out there are basically 3 classifications of being saturated. There is, of course, saturated. And this is where you're at the maximum. At the maximum amount of solute in the solution. there is unsaturated. This means more could be added. And then there is the supersaturated. And that's where there's too much. There's too much solute in the solution.
Can you scroll down a little?
Now, you want just the black stuff, Yadira?
Yeah, just the black. Thank you.
Okay. Yeah, not a problem. Now, there's a semi-common one if you pay attention to your childhood, where you have discussed unsaturated and saturated, and I'm going to show you a little bit of what supersaturated means. But saturated and unsaturated. Let's go back to old school. Mom doesn't want you to be a hyperactive little kid. She says, we're not going to have any sugared cereal. She gets you cornflakes. As soon as she turns her back, you immediately go to the cupboard, you grab the sugar, and you start pouring it onto your cornflakes. Now, if you only sprinkle a little bit, not a problem. That milk, the watery solution there, will dissolve your sugar, and it'll be fine, and you have a nice, mildly sweet cornflakes breakfast. If, however, you are angry at mother for doing that, you will grab that sugar and you will pour just a mound on top of it. You'll quickly mash it underneath the cornflakes before she comes back and say to yourself, I have outsmarted you. You have then made a very, very sugary situation, which makes you very happy. But you will also notice that by the time you get to the end of your cereal, there is still sugar at the bottom. What you've done there is you have allowed that milk to absorb as much of that sugar as possible. And then the rest of it just sits at the bottom of the bowl. So up until you just do a quick little sprinkle, not a big deal. You could probably add more and add more and add more. You're in the unsaturated place. Saturated, you'll know because you won't be able to get any more in. It'll just sit at the bottom. Now, there is a neat little plot that can be made, and that is everything has a certain amount of grams of solute that can be put into 100 grams of solution. And it is a function of the temperature. A typical plot like this, now remember, we said if it wants to go in, it'll go in. If we want it to go faster, we're going to heat it up. Now, part and parcel to that is that as you heat it up, you increase the amount that could actually go in. And a typical curve looks something like this, where the higher you get that the higher you get that temperature, the more you can put in. So now you can see perhaps why, as you increase the temperature, you make that stuff go faster. You make it go faster because you basically have given it more places to go. And when there's more places to go, it'll naturally go there faster. Now this line right here, this purple line that I've drawn, this is what we call the saturation line. And so at any given temperature, you can say, okay, I'm at this temperature right here. I can tell you exactly how many grams of that solute I can put in 100 grams of solution. Which means that everybody underneath the curve, this is the unsaturated area. So clearly, if I'm at that little orange area that I've said I'm at that certain temperature, if I'm anywhere down in here, that means I am unsaturated. That also means, though, that above that curve is what we call the supersaturation. So if I happen to have this much in there, I've got too much. Now, I do want to point out that we are doing grams of the solute per gram, 100 grams of solution. That's how it's defined. For the most part, we don't really think about this. We take a certain amount of salt or sugar or something like that, and we dump it into the water, and nothing seems to happen except for that solid just disappears. We don't actually notice whether or not there is a volume change. And it turns out that some things, especially sugar actually, if you take a cup of water, you can easily dissolve a 1/2 to 3/4 cup of sugar into it. And you're not going to come out with 1 cup of sugar water. If you start getting too much solute dissolving into your solvent, you will actually end up changing the volume. Most of the time, most of the things that we do as human beings, most of the thing we're interested in, we don't change the volume, but there are situations where you can. So again, since volumes can change, but mass does not, we always define it as grams per 100 grams. Nathan wants to know, how does that work with saturated and unsaturated fats? Ask me afterward. It has nothing to do with this, but it is the terminology that does borrow from this idea. So stay after and I'll answer it after the lecture. Now, hopefully you can see that if you wanted more to get into solution, you want more, you increase the temperature, and look, you can get more stuff in. That's exactly what's happening when you get your hot tea. You know that you can make your hot tea incredibly sweet if you want, much sweeter than you could iced tea. Now, some of you may also be asking yourself, well, if I'm dumping all that sugar into the water, dumping all that salt into the water, and eventually I get that pile of salt at the bottom, meaning no more salt, no more sugar can get into solution, so it's just falling straight to the bottom. The water's like, look, I can't hold anymore. You're going to have to sit this out. Then how do I ever get to that spot? Well, I've kind of already shown you. If I am at this orange temperature right here, if I'm at this orange temperature right here, but I want that much stuff in my solution at that temperature, all I have to do is increase the temperature to the blue, get up here, get that much stuff dissolved, saturate it out, and then cool it back down. And if I cool it back down and I do it right, and I do it very carefully, I can actually trick that solvent into keeping that amount of solute into it. I can trick it to having too much stuff. What does that look like? All right, do we have another question here? What's going on? Oh, Nathan says, okay.
So I have a question.
Is syrup an example of that? So Stuart, no, syrup is not quite super saturated. Syrup is getting close. So they do make it by heating it up usually. And you can make that syrupy mix for your mixed drinks and stuff. You're only heating it up to make it go faster into solution. Again, you can make those syrupy things by just taking your time and letting it slowly get in there and stirring. They heat it up to just make it get in there. If they super saturated it, I'll show you what would happen if you just decided to randomly pour your syrup. It wouldn't pour. I'll show you that in a video just a second. Go ahead, Reagan.
Yeah, I'm confused by the, so it looks like you lined up all your dots, which I didn't do. So you're saying if you put in more of the solute, which is the red one, you can put in more of the solute, but you also have to increase the temperature.
Yes.
And put in more solution.
No, you keep the solution the same. You still keep 100 grams of your solution, but what you've done is you've heated it up. And so if my original saturated point is right here, If I heat it up, guess what? I get to put more and more and more until I reach this point.
So if I have a cup of water or 100 grams of water, and I put 5 grams of sugar in, if I continue to, and I stir it and it dissolves, I can continue to put more sugar in as long as I'm going to increase the temperature.
If you are already at the maximum, yes. So you can do this at home. You can do this at home. You know what? Let me just show you. Let me just show you something, and maybe this will help.
Okay.
Let me see about this. Let me see about this little chat thing here first. Oh yeah. So, and this is something that if you have kids and stuff at home and you don't mind making a mess, you can do this. All right. Let's minimize the participants there, and let's do YouTube sodium acetate. That's all you have to do. You get this guy right here. This will be one of the ones I typically pull up. So if we look at this, what the person is doing, oh shoot, let's see if I can pause it. What the person is doing, and you can sort of see them right here in their little shadow here. They have what looks to be just a clear solution, just some water sitting there. What they haven't told you is they've taken sodium acetate. Very, very soluble. If you remember your solubility rules from like last week, sodium swims, acetate also swims, and they both swim very, very beautifully. You can get a lot of sodium acetate into water. Now, what you do is you dump a whole bunch in. You mix, mix, mix. You finally reach the saturation point. Then what you do is you heat it up very gently, and you put more in, and you put more in, and you put more in. And then you say, okay, I'm done. And I'm just going to let it sit there, and I'm going to let it cool. If I don't do anything to it, I'm going to trick that solution to have way too much solute inside of it. What this person is about to do is say, hey, solution, how would you like one more grain? Just one tiny little speck of sodium acetate. As soon as this person does this, the solution is going to look around and look for a place to put that sodium acetate. It's going to say like, yeah, I get it. Sodium swims, acetate, you want to swim too. Hey, why don't we give you a place to go swimming? And it suddenly takes a look around at the entire solution. And it gets real mad real fast because it says, wait a minute. I'm not supposed to have all of you in here. I have way too many of you in here. And much like that random house party where you only invited 10 people, but 100 showed up, once you finally realize that they're wrecking the place, you kick everyone out. And that's what's going to happen here with the sodium acetate. He's going to try to put one more speck in there, and the whole solution is going to say, hell no. Oh, I've never actually done it with the volume. That's kind of funny. So it's going to drop it in there on the end of the stick. And that solution is now saying all of that sodium acetate needs to go, and it needs to go now. And it's making sodium acetate crystals. Now, he's probably just barely into the supersaturated realm because it's taken its sweet time kicking everyone out. But every time it kicks one out, the solution is going like, oh, look, there's another solid. I should look for a place. It looks around and goes, there's no room. And it just is a daisy-chained effect that or a chain reaction that makes it basically kick everyone out of solution. And that was real time. How do I get out of here? I want to get, you can actually make it. I don't know where my escape button is because I'm on a 2-in-1. I'm trying to see if I can scroll to the one that I really normally like. That's a good one. Fun with sodium acetate. So again, they put little things on the end of toothpicks, went into solution. The solution is dumping it all out. Keep in mind, it's also reforming those sodium acetate bonds. And look at that, the temperature increased to 52 Celsius. Sometimes you don't even have to put a crystal in. When we were talking about the syrup there, Stuart, I've tried to make this sodium acetate solution. I have failed miserably over and over. mostly because I probably made it way too saturated. And even just the mere jiggling of the container will sometimes shock the solution to just come out of solution. So sometimes if you're super saturated like these guys are here, it will come out of solution just that fast. And again, forming bonds releases energy, and this is why sometimes it's called hot ice. I love this. They're actually going to make it crawl back into the beaker. That's always fun. And they'll go ahead and write with it as well. They must have had a little speck there, or maybe something just jarred it. So that's kind of cool. Let's see, I had a couple things here in the chat. Is molasses super saturated? No, I think it's just really saturated. Again, sugar can dissolve in water pretty easily. So if you go onto YouTube, you will find ways that you can take baking soda and vinegar and do this sort of thing, and it's fun at parties. It can get messy though. I'll just let you know that. Oh man, more things in our chat. What's going on in the chat? Is all the solute changed or just the extra that oversaturated it? Usually it kicks everyone out and says, please try again. Especially with the sodium acetate, you notice that he essentially took over everything. It was saying no and hell no and try again. Because as you start kicking more of it out, you basically start taking up more and more room, which makes the solute, or I mean the solvent, look like it has less and less places to put it. So usually everyone gets kicked out.
So in your party example,
all right, last thing to talk.
Now you have to go.
Say it again.
In your party example, it would have been like, you may have been invited, but because you brought too many people, now you have to go too.
Yeah, exactly. Everybody's out, right? Everybody, including the person passed out on the sofa. Sucks to be you. The last thing I want to talk about today is the mass percent. And this is the last time I think we talk about percents, but I told you we do it a lot. And again, it's just a part over the whole. It's the part over the whole, of course, times 100% to keep you happy. And really what we're talking about here is the mass of solute over the mass of solution. So that's your mass percent. And so a couple of examples here, just because it's easy to do it by example, is let's say I have 15 grams of NaCl dissolved in 85 grams or 85 mils of water. So simple calculation is simple. My percent of sodium chloride is equal to the 15 grams of sodium chloride over the 100 grams of solution. Of course, times 100% means that it is an easy 15% NaCl. Just to remind you that the 100 grams is the 15 grams of solute plus 85 grams of solvent. That's how you get that 100. Now, since many of you here are going into the health occupations field, in my latest trip to the ER a few years ago when I crashed my bike at ludicrous speeds into the back of a parked Honda Element, it was gloriously, what did Dan Clemens call it? Horrifically spectacular was his description of it because he was writing right behind me and watched the whole thing. While I was there, I actually grabbed a bottle of one of their saline drip solutions. And I was like, I'm going to use this as one of my examples. So how much salt is in 500 mils? We're going to go ahead and just nominally call this 500 grams of a 0.9% saline solution. So this is the standard IV solution that they might give you to stabilize the electrolytes in your blood, the salt levels in your blood. This is essentially what it looks like in your blood as far as its salinity, if you will. So the percent of NaCl is equal to the grams of the NaCl over the grams of the solution, which is our saline drip solution. We are actually looking for how much salt is there, so we're just going to multiply up, and we're going to say that the percent of NaCl times the grams of solution is equal to the grams of NaCl. And it should be noted that NaCl is actually a decimal, so it's 0.009. Right, percent is decimal. This is your 0.9%. We just move that decimal back a couple of places. Multiply that by the 500 grams of solution. And that will give us 4.5 grams of NaCl is in the saline drip. So if you were in some sort of weird zombie apocalypse, kind of like what we're having right now, and you needed to make a makeshift IV drip for somebody, you grab water. So what is that? 4 cups basically. You drop in 4.5 grams. That's not very much. Let's see, what is that in ounces? 28 grams in an ounce. So divide that by 4.5 by 28. Where's my calculator? There it is. So 4.5 grams divided by 28, just on the ballpark. So 0.16 ounces. Whew. Not very much. It's basically like a pinch. You wouldn't even know it's salty. But hey, you can save someone's life. Look, I just did something that mattered. We saved lives. All right. Any burning questions before I stop the recording and then hang out for the fun little stuff?
Can you just move up? I don't have a question. I just need to see the chart again. Please.
So which one?
The chart. I just.
How far up?
Yes.
Oh, you want to see the chart again? Yeah.
Yes. You can just keep that up.
Okay. Sure. Any other questions? I'm going to stop the recording, and then I'll do my esoteric questions for people.